Hoang, we will be talking about deep learning works in practice, but does it work in theory?
So, hello everybody. Thank you for your attention. So today I'm going to discuss deep learning and through the lens of algorithmic information theory. And I'm going to start with a simpler question: is why does deep machine learning in general work? And I don't know if you know about this, but this is a question that was already tackled in the 1950s by a guy that's worth mentioning in this environment, which is Alan Turing. So in 1915, his paper where he discusses the Turing test, Turing also introduces the idea of machine learning. Well, he called this learning machines, but it's the same. And he also provided a very compelling argument for why machine learning will eventually work. And I think this is one of, to me, maybe the most beautiful argument I know in computer science. And his argument was a Kolmogorov complexity argument, essentially. Kolmogorov had not invented complexity theory, Kolmogorov complexity theory yet. But essentially what Turing said is that there are tasks that are probably thinking about the Turing test, that requires a high Kolmogorov complexity algorithm to be solved. Like you will need to really write a lot of lines of code to achieve these tasks. And because of this, Turing says, we humans cannot write it. At least Turing says, I'm not good enough of a programmer in the sense that I don't write enough code per day in order to write billions of lines of code. So if you think that if you want to solve tasks, you need to write millions of billions of lines of code, then it's hopeless for humans to write millions of billions of lines of code. And so that's why Turing said, we need another way to produce high Kolmogorov complexity code than programming. And this was the idea of having machines writing this code. And they had to be driven by something, because if you just, it's easy to write, like you can just take a random piece of huge code. It would be of high Kolmogorov complexity, but most codes, very large codes, are extremely bad. So you need to be guided by the data, by something. And Turing says the data should guide the search for good high Kolmogorov complexity algorithms. So you can already think of machine learning as a way to explore high Kolmogorov, the space of high Kolmogorov complexity algorithms. So then in a few years later, a few decades later, another guy, Solomonov, came up with a solution for actually how to do this, how to let the data drive your search for high quality, high Kolmogorov complexity algorithms. And the key to do this is to let the data guide you through BAZEL. And actually, I came to this field through BAZEL. I wrote this book on the right called The Equation of Knowledge on BAZEL. And the trick, the key idea of Solomonov was to say, let's apply BAZEL, but to apply BAZEL, you need a prior. And the idea of Solomonov was to say, we're going to consider all theories that are computable, that are define a computable probability distribution. And based on this, everything essentially works out. I'm sorry for the it's in black on white. It's not ideal. I don't know why. Sorry. So there are two issues, however, with this that have to do with complexity, another kind of complexity, well, all sorts of complexity. The first thing is that the set of heuristics that you would want to consider, or Turing machines that define probability distribution, is uncomputable. So as a result, you cannot apply Solomonov's induction. But there's another issue, is that even if you could somehow have a no record that tells you which algorithms terminate, for instance, and even then you will not be able to apply BAZEL, because the time complexity would be exponentially long. So you cannot apply BAZEL for this other reason. And even if you try to restrict the set of Turing machines that you want to consider, which is, by the way, what is done with neural nets. Essentially, neural nets, you can see this as considering a subset of all computable theories. And interestingly, you can even consider algorithms that whose computation time is predetermined, if it's a fixed neural net. That's a way to fix the issue with the uncomputability of the set of computable theories. Even then, you would still need a faster way to search, to explore this space of algorithms than BAZEL. And that's how people came up with stochastic gradient descent. And you can really think of stochastic gradient descent as a very effective tool to explore this space. that's so effective that it's linear time essentially in the number of data points that you have. And that's extremely important when you have like millions of billions of data points. Now, so that explains why like machine learning would work, and even like neural networks in the way it works today works. But it doesn't explain why deep learning in particular works. In particular, you still have an option. You could choose to go with a shallow neural nets, or like for instance, a logistic regression or linear regression, or you could go with deep neural nets. In a sense, when you're choosing one over the other, you're choosing a bias in an inductive bias in your learning theory. And so, like empirically, we see that deep neural nets perform better. But why so? What is the reason behind this? So there are many papers that are, well, several papers that try to answer this, and it was mentioned in the previous talk. Essentially, there are, like this paper found out that there are some functions that are actually efficient to compute with a deep neural net, meaning that you need a few parameters. But if you want to compute them with short neural nets, with shallow neural nets, then you would need exponentially many parameters. So there are functions that are easier to describe with deep neural nets. So that's a way to distinguish the two classes of functions that are computed. But I would argue it's not necessarily the fundamental reason. What you're just saying is that these two classes are different, have different inductive biases. And I would argue that the key reason why, if you want to really understand why deep neural nets work better, you have to look at the data. Because this data is what's guiding the training. And in particular, the complexity of this data is explaining why some inductive biases are performing better than other inductive biases. Now, there are multiple ways of measuring data complexity. One of them is Kolmogorov complexity. I'm sure you've heard of in the last 2 days. But another measure of complexity, which I'm going to discuss today, is the notion of Bennett's logical depth. Essentially, you can think of this as a time complexity measure. You can think of this as the decompression time. So with Kolmogorov complexity, you have this idea of take the data, you try to compress it. But then you can ask, how long does it take to decompress the data into the original data? This time is Bennett's logical depth. And what I would argue is that real world data have both high Kolmogorov complexity, which is the reason why we need machine learning, but also seems to have a very large logical depth. As an example of things that require large logical depth to be well, the kind of data that have a large logical depth, arguably all of mathematics is this kind of data. If you consider mathematics or just like some beautiful theorems, some of these theorems are very easy to describe. So they actually have small Kolmogorov complexity, but sometimes finding the proofs can be extremely long. And even sometimes just reading the proofs itself can be extremely long. So it takes a lot of time to work out the theorem. So that's the idea of logical depth. As another example of logical depth, you can think of fractals. Fractals are usually easy to describe in the sense that you have this iterative process that you can describe in a few lines of code. However, if you want to actually produce the fractal, to decompress this code, it takes a lot of computation time, a lot of iterations. And so, as you probably know, there's a lot of fractal structures in the world. And this suggests that if you want to understand this, then you need some structures that have encoded an inductive bias towards large logical depth. And this is exactly what provides what deep neural networks provide as opposed to shallow neural networks. Interestingly, there are some papers that show this connection between fractals and deep neural nets, even though it may not be extremely surprising if you think a bit about this. But these two papers by some researchers at Stanford or Google really show that, in a sense, the complexity of what's computed by a neural network measured in terms of some measure that's like close to fractal measure of fractality. This kind of complexity grows polynomially with the width of the neural network, but exponentially with the depth. So if you want to get a large complexity in this sense, you will need to go with depth rather than width. So essentially what this talk is about these two conjectures. Is the fact that real world data have a large Kolmogorov complexity. And by real world data, I really mean like the kind of data you download on your computer. So you can think of all of the data on the internet or the kind of data that you would get if you looked at all of the papers published in science, or you can think of all of Wikipedia, for instance. This kind of data has large Kolmogorov complexity. So if you want to train something that learns really this data, it will have to have a large Kolmogorov complexity, at least billions of bits, maybe like a lot more. And the second conjecture, which is kind of like, if you're being Bayesian about this, like the kind of reflections we have today should increase the probability of the second conjecture, is the fact that real world data also have a large logical depth, which means that you should favor some deep learning. Yes?
When just with data in the real world, the amount of information required to express it scales with the size of the data set.
Yeah.
So like how does that relate to the statement that we have fixed?
Yeah, so it's not a precise conjecture, right? So what I would say is that if you take some real world like data sets, so Wikipedia, for instance, then the complexity in terms of logical depth of this data would be large.
So you just mean that things that are never like almost trivially simple, that they should be described in intensive. For example, like one Wikipedia page obviously has a less complexity than the whole of Wikipedia. And then I could look at a paragraph.
Yeah, of course.
And then I would get small.
Yeah, of course. So like, especially if you have a Kolmogorov complexity larger than a billion bits, and you need an input that's at least billions of bits, right? So, but let's say the kind of data you would really want to describe in a world. I mean, like all of the internet is like something nice to have. Yeah, there's a small technicality here. Is actually what matters is not actually logical depth per se, because if you think about this, a wide neural network still need to do all of the computations. The thing is that if it's wide, then the computation is parallelized. So what really matters is actually non-parallelizable logical depth as opposed to just logical depth. And this relates to a famous conjecture in complexity theory, which is the prime P versus NC. NC stands for Nick's class, if you don't know about this. I'm not going to into the details, but essentially the question is asking, can asymptotically deep problems be asymptotically parallelized efficiently? In particular, well, P is like the polynomial time problems, and NC is like you would like logarithmic or pre-logarithmic time computation with a polynomial number of processes. I think the consensual opinion out there is that these two are different, and this would suggest that there are things that are non-parallelizable, which would fit with the conjectures. Okay, so one thing I do want to touch on, most of the talks is already done, but one thing I do want to touch on is the implications of all of this for AIfix. So I am extremely engaged in AIfix. I think it's extremely important now that algorithms are deployed on very large scales. You can think of the YouTube algorithm, for instance, that's influencing billions of people's beliefs, creating all sorts of hate speech and geopolitical tensions. So I think it's urgent that we think about AI safety and AIfix. And unfortunately, what we've talked about today has implications on AIfix and not necessarily good news. So one thing, for instance, is that there's been a lot of discussion about this, saying that if you want to have ethical algorithms, the algorithm needs to know what's ethical, what's a good video to recommend. And unfortunately, this is a difficult problem. Like just describing AIfix seems necessary to solve this, but ethics itself seems to be of a very high Kolmogorov complexity, which means that you cannot write it yourself, that you're going to have to do machine learning because you cannot write billions of lines of code. And the other thing is that it also seems to be of large logical depth, meaning that like you would favor like things that are very slow to compute. And maybe this relates also to like the system 1, system 2 in psychology, the fact that we have instinctive preferences, but maybe these are not necessarily what you would prefer if you thought longer. So there's this distinction between preferences and volitions. And another consequence of this is that the more ethical algorithms may be very slow to compute. And this doesn't fit with the needs of actually deployed algorithms. So you can think of self-driving cars, for instance, or again, with my example of YouTube algorithm that needs to provide answers in milliseconds. So this raises a few issues for safe and ethical AI research. So first of all, if you want to explore high Kolmogorov complexity spaces, then you need to do machine learning. And if you want to do machine learning, you need the data set. And a large data set that itself contains the Kolmogorov complexity of ethics, which means like billions of bits, something like this. So a very large data set that is about ethics, like that contains ethical judgments. Today, we're nowhere near having these large data sets of human ethical judgments. So we really need to work on this if we want to create safe and ethical AI. The other thing is that because we want heuristics, because like most of the algorithms that actually run have to run very fast, we are going to have errors that are not necessarily due to the learning, but are due to the fact that we want heuristics. And this means that we need to be able to handle these errors as well. And this prompts us to another field, which is the field of robust learning and adversarial learning, meaning that we need to be robust to such errors and even attacks, for instance, attacks on the data sets, which increase as the data sets increase in size. So actually for the last 3-4 years, this has been my main focus. Like, we've been working a lot on making algorithms safer. And this means building this data set. So we have this website called tournesol.app, where we're trying to engage a lot of people in comparing YouTube videos to understand what people consider what videos people consider to be ethical to recommend on large scales. We're also developing algorithms, again, with this idea that they need to be fast. And so we also have ways to control the uncertainties and so on. And also we have research on the machine learning security with papers at NeurIPS and ICML. So I just want to conclude by saying that we have sort of this overarching goal, which is to design a computable moral philosophy. I think a lot of moral philosophy so far fails to account for the constraints of computability. And this is a big issue. Clearly in AIfix, if you want to do ethical algorithms, you need them to be computable. But I would argue computable moral philosophy is also about leveraging all the things we know from, for instance, algorithmic information theory that have implications on moral philosophy. And I've sketched a few things already with Kolmogorov complexity, logical depth, but also like complexity, time complexity theory, distributed computing, Byzantine resilience, and stuff like this. And I think it's high time that moral philosophy gets input from algorithmic information theory. And with this, I thank you for your attention.
Yes, so you talk about I guess Kolmogorov complexity as a set of large moral judgments. That was very interesting. But does that sort of presuppose a kind of democratic definition of morality?
Yeah.
Most people think it's moral, but that's what defines moral. Is that your view?
Yeah, that's an excellent question because we've been moving more and more towards this direction. So we're seeing more and more machine learning as a voting system. If you think about this, whenever you like a video on YouTube, then you're voting for this video to be more recommended. Whenever you produce text, and this text is going to be reused by GPT-3 in its training, you're voting for this text to be repeated by GPT-3 in a sense. So we think of learning algorithms as voting algorithms, and this means that you need to apply the tools from social choice theory to combine them with machine learning. So one of the ideas we had, one of the important ideas that I think we had is the idea of one person. So traditionally it's like one person, one vote, but what we're trying to have is more like one person, one unit force. So this has to do with like in SGD, you have this gradient that you give, and essentially one person can only provide a gradient that's of unit norm, and that way we have both safety and fairness. And also we studying all of this under the angle of incentive compatibility or strategic proofness, for those who know, like, or the contributors incentivized to produce honest inputs.
I don't necessarily have an alternative, but historically there are plenty of times the majority of things of what was moral was not what we thought. So how do you deal with that?
Yeah. So there are different things you can do about this. So first of all is to try to better understand the distinction between preferences and volitions. So typically when people provide the judgments on our platforms, you can see the amount of time they spent doing so. And you can also try to estimate their expertise and so on. So we try to leverage this to better understand this kind of distinction. And another thing is, well, when judging, for instance, a video about vaccines, maybe you want to value expertise about this. This relates to another classical point by Condorcet, who asked whether the judgment of a judge was better than the judgment of the jury. And he assumed that people in the jury were independent, and which is like a disputable assumption. So we're trying to come up with more realistic assumptions to measure all of this. But these are different, very important things that are not trivial.
Thanks for the talk. Quite good that people talk. I had a question about the complexity, so the moral complexity and logical depth of moral judgments. Could it be that it's only apparently complex, apparently large? Imagine that someone comes next year with a new explanation of the human condition and says, okay, oh, that's just happened. The same way as some people claim that all novels that you buy in the railway station are just always the same story with slight variation, like Noam Chomsky saying that all languages on Earth are pretty much the same language. Could it be that this complexity is only apparent and that you be wrong in that case to say that it's hugely complex?
Yeah, so an argument for, which I think is quite compelling for why it's necessarily complex, I think, is that one thing you would want to encode is that torturing cats is bad. I think we agree, maybe. Torturing cat is bad, and so as a YouTube recommender, you don't want to recommend videos of people torturing cats. The problem is that if you want to formalize this, you need to be able to tell to the algorithm how to recognize cats in a video or in an image. And it's been like 70 years that people have been trying to do this, and no human has ever been able to program an algorithm to detect cats in an image with a high accuracy. And the only way we solved this was to train algorithms to detect cats based on data. And these algorithms have a large number of parameters, so they are of non-trivial Kolmogorov complexity. And I think a lot of the concepts that are like this require a larger Kolmogorov complexity. Yeah.
I just on that, I mean, the number of parameters, not necessarily the proxy. Very redundant
yeah, it could be, but when all of the algorithms that successfully detect a cat to this day have large numbers of parameters, I think it suggests that it's hard to compress these algorithms.
Well, actually, you can compress them after the day. There's evidence that the large amount of parameters is necessary for learning, but not for scale them after learning. Usually you end up with about 5% parameters. You want to say 4%.
Yeah.
5% is still the same.
Yeah, I mean, I mean, the better argument is that no human has been able to program this. I mean, if the algorithm was like within reach of human programming, and people have tried a lot. I mean, yeah, so.